differential equation for k number of components. Therefore, uh, it is basically referred that we should go for a computational method through which we can solve the MLE estimation, and that is basically the EM algorithm. And the EM algorithm also tries to find these parameters with a basic notion of maximum likelihood estimation, because that is the main funder to evaluate the parameters. Because through maximum likelihood estimation only, we can evaluate the parameters. So therefore, EM algorithm is based on the principle of maximum likelihood estimation. However, the only concern over here is this is uh, a computational method. So this is the main point. So EM algorithm is a computational method to solve the uh, maximum likelihood estimation for this k number of components that is there in case of Gaussian mixture model. Okay. So the next question states that each component in GMM is characterized by. So already we have written that what is GMM. So GMM can be written as summation ik normal distribution of x given the parameters, and the parameters are the mu k and sigma k, and k is running from k equal to 1 to capital K. So therefore, you can see the not. It is basically you have the weighting or mixing coefficient. Then you have the normal distribution. Considering that your x is a d-dimensional data, so therefore your normal distribution is specifically a multivariate normal distribution. Multivariate normal distribution, and which is also parameterized by mean and covariance matrix. So in general, your covariance matrix basically comprise the weighting factors or the mixing coefficients and the normal distribution, and itself in the normal distribution it is basically characterized by the parameters of the normal distribution. So in general, as I am considering that this is a multivariate distribution, so therefore your distribution comprises mean and covariance matrix. So in general, your GMM comprises of three main factors. One is weighting factor and mu k and sigma k of multivariate Gaussian distribution. So in this case, they have only given mean and covariance matrix. So this is the correct answer. Mean, median, mode. So we do not have median and mode. So this is incorrect. Then skewness, kurtosis. So uh, uh, mean is basically called the first order statistical moment. Variance is called second order statistical moment. And this skewness and kurtosis, these are the third and fourth order statistical moments. However, in case of Gaussian, or normal distribution, specifically normal distribution, if it is not a skewed normal distribution, it is basically following the basic structure of the bell-shaped curve. So then your normal distribution is parameterized by mu and sigma square, right? So therefore, you do not have this skewness and kurtosis inbuilt into the equation. So therefore, and obviously, as because GMM is comprising of the normal distribution of the Gaussian distribution, which is parameterized by mean and standard deviation. So therefore, this skewness and kurtosis are obviously not there in the equation. So uh, so far as variance is concerned, various standard deviation all are related, but skewness and kurtosis, these are not present in Gaussian mixture model. And the last one is standard deviation and correlation coefficient. And correlation coefficient is also actually not present. So what is correlation coefficient? So this is CC is basically the equation of CC is covariance matrix of XD divided by variance of XD, variance of XD. So this is the correlation coefficient formula. So again, correlation coefficient is not at all related in this case in the Gaussian mixture model equation. So therefore, this is also not the correct answer. So mean and covariance matrix is the correct answer for this particular question. Okay. The next question states that which of the following statement is true about Gaussian mixture model? So we can go by the process of elimination while solving some of the questions. So Gaussian mixture model already we have talked about. For example, if you have a data like this, you have a data distribution like this. So this you can actually model it using a single Gaussian. So this you can model it as using single Gaussian function. And these are the equal energy contours. But let's say you have a data looking like this. Let's say you have a continuous data which basically looks like this. So now just by visualizing the data itself, you can understand the distribution does not seem to be a generic structure of Gaussian. So what you can do, you can piecewisely create the Gaussians like this. Now you can see that instead of using a single Gaussian, you can see this is Gaussian 1, this is Gaussian 2, and this is Gaussian 3. And So n, x, sigma k and mu k, and you have weighted them using some weighting factor sigma k, I k, and then you can do the summation over k. So this is how you can use the definition of Gaussian mixture model to generate a model for a difficult data distribution. So there you can fit piecewise Gaussian distribution to create the probability density function for the data set. Now the point is, given these particular statements, we have to understand that what is the uh, true statement regarding Gaussian mixture model. So already we talked about in the first slide that Gaussian mixture model is basically comes under the regime of unsupervised learning. So unsupervised learning means there you have only the data, you do not have the labels. So if you have only data and you know nothing about that data, so if you normal human tendency is basically if you know nothing about something, you try to group the things. Now, based on that, grouping or clustering comes under the picture of unsupervised learning. And over here, if you see that you had initially a whole data, and from the whole data, you are trying to cluster the data through different Gaussian functions. So GMM is basically used for clustering problems. So GMM is only used for the clustering problems, and which comes under unsupervised learning approach. So thereby, this GMMs are only used for regression tasks. That is incorrect. It should have been the clustering task. GMM is not used for regression tasks. It is used for clustering tasks. So therefore, the option 1 is incorrect. GMM can model data with a single cluster. So over here, I have shown that this GMM is creating 3 different clusters. So this is cluster 1. Then you have cluster 2. And then over here you have cluster 3. So now you can understand that GMM can cluster the data by fitting multiple Gaussians with a linear combination of it. So thereby stating the GMM can only do a single cluster, so that is incorrect. Okay. And the GMM, in case of GMM, the main fundamental property is basically this is a, you can see that this is a probability distribution function. This is nothing but a sum, the weighted summation of probability distribution function. So the probability distribution function is a statistical process. This is a statistical process, whereas a neural network based approach is often called black box, relates with heuristic approach. So over there, you go by learning based algorithms. For example, we have seen gradient descent based learning method. So neural network basically shows the property of black box nature as because we use heuristic based learning approach over there. But in case of Gaussian mixture model, we have in-depth mathematical analysis. We have statistical, as because it's a statistical process, I can formulate the Gaussian and I can do each and every process mathematically. I can prove each and everything mathematically. So therefore, there is nothing called black box type of feature is there in case of Gaussian mixture model. Rather in neural network, as because I specifically I cannot explain that how the neural network is basically learning, as because we are using some sort of heuristic based method. So thereby GMMs are not neural network based method because we have deterministic mathematical approach, and in general that mathematical approach basically leads to the statistical process. Therefore, this is also incorrect. So sort of by elimination, you can see that uh, option C is the correct answer. Okay. So the next question states that what does each component in Gaussian mixture model represent? So if I just uh, rewrite the GMM concept again, so it is pi k normal of x given mu k sigma k, and it is running over K. So data point in the data set, so this is not relevant. Principal component, Gaussian mixture model has no relation with principal component analysis or something like that, PCA. A cluster center. A cluster center is basically referred as the mean of the cluster, right? If you have a data point, data cloud, you take mean, so that will give you the centroid or the center of the cluster. But is it the only thing that is basically referred by Gaussian mixture model? We know that Gaussian mixture model comprises the Gaussian distribution, which is parameterized by mu k. But is it the only thing? So let us now see the next option, a Gaussian distribution with its mean and covariance. So this is the complete answer. So a cluster center, that is in some way it is correct because it is referring the mu k. However, it is not only the mu k that basically is the constituent factor of Gaussian mixture model. Rather, Gaussian mixture model comprises both mu k, that is the mean of the normal distribution or Gaussian distribution, and the sigma k. So sigma k is basically the covariance matrix of the Gaussian distribution. So therefore, this is also incorrect. A Gaussian distribution with its mean and covariance is basically the correct answer for this particular question. Okay. The next question states that let there be 10 data points. Let there be 10 data points. -1, 27, 31. So they have given till 12. So there are a set of data points been given. Use k-means clustering for 3 iterations to cluster them into 3 clusters. The initial labels have been given. So they have given the initial label to start with. So you have 3 particular groups, group 1, group 2, and group 3. And they're asking that after 3 iteration using k-means clustering, what would be the labels? Okay. So in this particular case, let us now start with the solution. So this question is pretty long. We need a pretty long iterations that we have to compute to get to the answer. So let us start first depicting the data set. So the data set is basically containing the data as -1, 27, 31, 2, 59, 3, 61, 34, 0, and 12. And the labels In the first instance is 1, 1, 1, 2, 2, 2, 3, 3, 3, 1. Fine. Now, as because they have given the labels in the first hand, so what we can do, we can actually think that these three data basically belonging to class 1. The last one also belongs to class 1. So I can create, so you have the data for class 1. So I am writing data subscript 1 is -1, 27, 31, and 12, right? Which belongs to class 1. So this is the data cloud that they have given for class 1. So what would be the centroid of the data cloud? So centroid of class 1 data cloud is -1 plus 27 plus 31 plus 12 divided by divided by 4. So I am basically taking an average of the data points. So if I take the average, my average is basically coming as 17.25. Similarly, centroid for data 2 class is equals to, so now I am not illustrating this type of thing again and again. So this is for the first set. For intuition, I just have wrote. Now I will directly write the value. So 2 plus 59 plus 3 divided by 3. So if you solve this, it will come as 21.33. Then centroid 3 equals to 0 plus 61 plus 34 divided by 3. So this will come as 6131.66. So now you can see you have got the three different classes, and corresponding to each of the class you have got the point clouds, and from the point clouds you can get the centroid of the data. Now we are now at a position to start the iteration. So you have to pre-compute the centroids of each of the data cloud. And now we can see, we can reassign each of the data point based on the fact that whichever point is basically lying closer to each of the centroid. So let's say data point 1, if it is lying just beside centroid number 1, we will assign that data 1 belongs to centroid 1. If data 1 belongs to, if data 1, if the distance, Euclidean distance between centroid 2 and data point 1 is the lowest one, then we can say that data point 1 belongs to class 2, as because the centroid is near or centroid is lying in vicinity to the data point 1. So using this concept, let us now start the iteration 1. So iteration 1. So what we'll calculate, we will calculate the distance as the Euclidean distance. Now Euclidean distance, we know that it is x1 minus x2 whole square, and over here we only have single dimensional data, so we do not have the y dimension, so therefore only x1 minus x2 square. So therefore in case of single dimension, if you just do the Euclidean distance, this is same as, so Euclidean distance we also call it as L2 distance. It is same as absolute distance x1 minus x2, so mod of x1 minus x2, which is L1 distance. Mind it, this is only true for the single dimensional case. If you go to the higher dimensional case, this will not be true. Because over here you can understand that uh, x1 minus x2 squared will give you the positive entity. And then you are taking the root of that, so we'll get the same value. So that means mod of x1 minus x2 you will get. And mod of x1 minus x2 is effectively the L1 distance. And Euclidean distance is the L2 distance. So for the single dimension case, Euclidean distance or the L2 distance basically reduces down to L1 distance or the absolute distance. Now, based on this, now we have to calculate for each and every point that whether it is lying in vicinity to centroid 1, centroid 2, or centroid 3. So now let us solve this. So let me name this distance operator as phi. So the distance I am abbreviating it using the phi operator. So phi 0.1. So in our case, 0.1 is -1, comma centroid 1, C1. So in this case, centroid 1. So this is C1. This is C2. And this is C3. So phi of P1 comma C1 is basically the I can write Euclidean distance, but already we have seen that Euclidean distance boils down to L1 distance. So I can just write it as -1 minus the centroid one is 17.25. So 17.25. So I just have written this particular thing x1 minus x2. So over here x1 is P1. So that is -1 and x2 is 17.25. So minus 17.25. So effectively it is 18.25. Okay. So now I will just write it. I will just scale it up for the other cases. So in the next case, it is 22.33. Then 5 P1 comma C3. So if you solve this, you will get value of 32.66. So now from these three distance, so we have calculated the Euclidean distance or L1 distance between the point 1 and centroid 1, centroid 2, and centroid 3. And from the distance measures, we can see that P1 is lying in vicinity to C1 or the centroid one. So thereby I can say that P1 belongs to omega 1. So let us consider this 1 means omega 1. Okay. So this is for the first data point. So similarly, we have to do this for all the data point ranging from -1 to 12. So that is why I was saying that this question is pretty long. So now let us solve for the other cases as well. So 9.75 pi P2 C2 is 5.67. Then phi P2 C3 is 4.66. So from this, you can understand that this basically belongs to P2 basically belongs to omega 3. Now let us solve for the other cases. Oh, sorry. So let's say P3 C1 by P3 C3, sorry, C2 by P3 C3. So this is, if you solve this, you will get 13.75, then 9.67, and then 0.67. So again, you can see that this particular P3 belongs to omega 3. Then phi P4 C1 by P4 C2 by P4 C3 is equals to, so I can write it as 15.25, 15.25. Then I got 19.33. Then I got 29.67. So from this, I can say that P4 belongs to omega 1, because you can see you have got 15.25, which is lesser than each and every case, each and every other cases. Then I can write for P5 C1 by P5 C2 by P5 C3. And if you just evaluate this, you will get the following values, which are uh, the fifth case. One second. So this is 41.75, 37.65, 27.33. So this boils down to P5 belongs to omega 3. Then the next one, 5P6 C1 by P6 C2 by P6 C3, which is equals to 14.25, 18.33, 28.67, which says that P6 belongs to omega 1, right? Now I can take another page. So I will just copy some of the things from the previous slide. Uh, so 5 in the last one we solved for P6. Now let us do for P7 C1 by P7 C2 by P7 C3. So if you solve this, you will see it as 43.75, 39.67, 29.33. So P7 belongs to omega 3. By P8 C1 by P8 C2 by P8 C3 equals to 16.75, 12.67, 2.33. P8 belongs to omega 3. Then 5 P9 C1, P9 C2, P9 C3 is basically reduces to 17.25, 21.33, and 31.67. So this reduces P9 as omega 1 And the last one, P10C1, P10C2, P10C3 as 5.25, 9.33, 19.67, P10 belongs to omega 1. So therefore, after iteration 1, the labels are, so I'm writing label 1. Initially, you had label not, so which was the starting label that you've been provided with. Now, after iteration 1, the labels have been changed and the current label order, is 1, 3, 3, 1, 3, 1, 3, 3, 1. Everything, so that you can observe from here as well. So the last four I can just show you from here. 1, 1, 3, 3. So 1, 1, 3, 3. So there is a comma over here. So now you have got the results till the first iteration. So after first iteration, as you can see, the data label has been changed. So therefore, the centroid has also changed now. So now the after iteration 1, the updated centroid. So centroid 1, centroid 2, and centroid 3 is equals to, so from here you can see that uh, so the first point, so -1, then the fourth one, so 1 plus 2 plus 3 plus 0 plus 12 divided by 5, which comes down to 3.2. And for this case, for class 3, it would be 27 plus 31 plus 59 plus 61 plus 34 divided by 5, which is 42.4. And surprisingly, you will see that there is no uh, data which basically comes under label 2. So that means for group 2, there is no data after iteration. Sorry. So after iteration 1, you can see that there is no label or there is no data which basically comes under group 2. So what would be this centroid thing? So the rule of thumb is you have to consider this centroid for that particular class which has got no data point after iteration 1. You have to consider the previous centroid value. So before starting iteration 1, what was the centroid value over there? The centroid value was 21.33. So in this case, the value should be 21.33. Right. So given this, now we can start iteration 2. So we will start iteration 2 now. And in the previous case, I wrote the illustration in bit detail, but in this particular case, in iteration 2, I will not write all these phi operator values. Rather, I will just directly show you that whichever data points belong to whichever classes. So for instance, I will show for 2 or 3 cases, and then I will directly write that whether the data point belongs to group 1, group 2, or group 3. Okay. So I can again copy some of the things. 8.3, so you can, yeah. And the current label should be, so this is the current label, so I can just copy paste this particular part. So 1, 3, 3, 1, 3, 3, 1. Last में दो 1 है. So 1. Now let us do for second iteration phi p1 comma c1. So also I have to write the c1 c2 value. So c1 is now 3.2. C2 is the previous one, so that is how much? 21.33. And your C3 is 42.4. So now let us start solving this iteration 2. So phi P2, sorry, P1, C2, phi P1, C3. So if you solve this, you will get 4.2, 24.2. Sorry. So this is what you will get, 22.33 and 43.4. So from this, you can understand that P1 belongs to omega 1. Then you can see that for P2, you have 27, right? So P2C1, phi P2C2, phi P2C3 will basically give you 24.2. Then you will get 5.67 and 15.4. So from here, you can understand that P2 belongs to omega 2. By the same logic, phi P3 C1, phi P3 C2, phi P3 C3 is equals to 27.8, 9.67, 11.4. And this will actually give you P3 belongs to omega 2. So over here it was L1, right? Then phi P4C1, phi P4C2, phi P4C3. So I'm not going to write these things again and again. because anyway, this is quite intuitive. So see, for 1, 2, 3, we have done the detailed illustration. So in this case, your data value is 2. So data value 2 means it is residing near to 3.32. So P4 belongs to omega 1, right? Then uh, now let us see about what is P5 is. So P5 is 59. So 59, obviously, it is lying besides C3 because distance between 59 and 42.4 would be the lowest one rather than the other two cases. So it will be omega 3. Then P6. So for P6, the value is 3. So obviously it is residing beside 3.2. So I can directly write it is belonging to group 1. Then P7 belongs to, so P7 is 61. Again, 61 is residing beside 42.4 because in other cases the distance value will be higher than the C3 one. So therefore it belongs to omega 3. Then P8 is 34. So 34, uh, let us see the distance between uh, 34 minus 21.33, it is giving 12.67, and for 42.4 minus 34, it is giving 8.4. So if I just start writing the updated labels, so I have got 1, comma 2, comma 2, comma 1, comma 3, from uh, 1, 2, 2, 1, 2, 2, 1, 3, 1, 1, 3, 1. Then again I have got 3. Okay. So I'm left with P8, P9, P10. So P9, we can see it is 0. So it is near to omega 1. P10 is 12. So for the 12 case, you will get 12 minus mod of 12 minus 3.2, mod of 12 minus 21.33, mod of 12 minus 42.4. So obviously uh, this will not give you the you don't have to bother about this. So rest of the case, let me just see. It is 8.8, and in this case, this is 21.33. So this is 9.33. So from here also you can see that P10 belongs to omega 1. So this is omega 1, and P8 belongs to omega 2. Fine. So therefore 3132111. Right. 1 second. Uh, for P8, let me just recalculate it once because 5P8 comma C1, 5P8 comma C2, 5P8, sorry, 5P8 comma C3 is equals to, so you have 34 minus 3.2, which is 30.8, 30.8. Then you have 21.33, which is 12.67. And then last one you have 42.4, which is 8.4. So sorry, P8 would be belonging to omega 3. So that means your current level is 122, 131, 3311. So this is after second iteration. So after second iteration, you have got this. So your centroid value will again update. So centroid 1, centroid 2, centroid 3. So I don't know why they have given this type of question for 3 iteration. A person will take 1 day to solve this particular question. Ridiculous. So one has 1, 2, 3, 4, 5. So divided by 5, divided by 1, 2. तो दो ही डेटा है इसमें, so divided by 2, and for the last case it has 1, 2, 3. So it has 3 data. So 5 2 7 3 10. Okay. So for centroid one we have -1. Then the fourth data is 2. Uh, then we have the sixth one, that is 3. Then we have the last two, so 0 plus 12. So I think this is same as the previous one, -1 plus 2, 0. Yeah. So this is again 3.2 is the centroid. Now let us see what about centroid 2. So centroid 2 will now change because now we have got some other data points over here. So for the second one, it is 27 plus 31. So 27 plus 31 divided by 2, it is actually 29. Fine. And the centroid 3 is now for centroid 3 last is 61 plus 34. 61 plus 34, and the 61, 34 and 59. So 59, 61 and 34, which basically reduced to 59 divided by 3. So this is 51.33. So I will just copy this part. So this is the data, and we have to take the labels as well. So let me just copy the label part. Very monotonous. Okay, now we can start solving for third iteration. So C2 and C3 is 51.33, and C2 was 29 actually. So C2 is 29. So now we can actually start solving for third iteration. Third iteration. So for third iteration, if we start solving for P1, it is no doubt it will be omega 1. P2, is 27 and this is closer to C2. So this is omega 2. P3 is 31. So again 31 is closer to 29. So omega 2. P4 is 2, which is near about your omega 1. Then you have P5. So P5 is 59. So obviously it is near to C3. So omega 3. P6 is 61. P6 is 61. No? 1, 2, 3, 4, 5, 6. Sorry. I think I have missed some data. 1 के लिए हो गया, 27 is done, 31 is done, 1, 2, 2, then 2 it would be 1, then 59 is, yeah, so P6 is 1, 2, 4, 5, 6. Yeah, P6 is near, so P6 is near C1, so therefore it is omega 1. P7 is 61, so 61 is near 51. Near 29. Sorry, so it would be omega 2. P9 is 0. So 0 is near about C1, so omega 1. And P10, again, it is near omega 1. So therefore, if I just now write L3, L3 is 1, 2, 2, 1, 3, 1, 3, 2, 1, 1. So 1, 2, 2, 1, 3, 1, 3, 2, 1, 1. So this is the correct answer. And now based on this, what would be the centroid value? Current centroid value. So current centroid value would be -1. So centroid 1, centroid 2, centroid 3. So centroid 1 would be -1 plus, it would be 2 plus 3 plus 0 plus 12 divided by 5. So again, it would be 3.2. The second case, now we have update. In the previous case, we can see that there was two data which were belonging to class 2. Rather, in this case, after updating with iteration 3, we can see that we have got another data which belongs to class omega 2. So therefore, I can write it as 27 plus 31 plus 34 divided by 3. So the answer is 27 plus 31 plus 34 divided by 3. So that is equals to 30.66. And the next one is you got 3 over here. So 61 plus 59 divided by 2. So 61 plus 59 divided by 2. So you will get 60. So your centroid is 3.2, 30.66 and 60. So I can copy this part. So this will help you in the next page. Okay, so from the above question, find the centroids after third iteration. So already we have done in the previous page. So let me just cut this. So from the previous page, we had actually evaluated after third iteration what would be the data labels, and corresponding to the data labels, we have also evaluated what would be the current centroid, that is centroid 1, centroid 2, and centroid 3. And we got that the centroid 1 boils down to 3.2, centroid 2 is 30.66, and centroid 3 is 60. So therefore, let us just scan the solution. So 3.2, 30.67. So they have just taken the approximation, and then it is 60. So therefore, it is the correct answer. Rest of them are incorrect. Okay. So let us just wait for 2 to 3 minutes, and then I will start again. Okay, so the next question states that how does k-mean initialize cluster centroids? Okay,
Sir,
so
excuse me, sir.
yes,
Sir, I have one doubt.
yes,
So you have solved this clustering problem, sir, with the initial labels given. If suppose
yes.
initial labels are not given, means how we can solve, sir?
Yeah. So see, these all of these problems are basically meant to be solved using computer algorithms, right? So starting from SBM algorithm, random forest algorithm. So that is why whenever you do or whenever you read anything, any literature about machine learning, deep learning, even in this question, see this particular question, how does k-means initialize cluster centroids? So in the first question, in the previous question, they actually have given the initial labels. And based on the initial labels, we started calculating the centroids. So what if your question is rightly, you are right, correctly asking this question that what if the initial labels were not given? So at that condition, we were not able to calculate the centroids. So for that, actually, what computer algorithm does is it initializes the labels randomly. So what it does, computer algorithms generates a initial label randomly. So it may so they have given this kind of thing. So the computer algorithm may choose directly, let's say 1 comma 2 comma 1 comma 3 comma something like that. It can choose a random sequence, and through this random sequence, you start solving the clustering problem through an iterative process. So in general, what happens through, as because we solve these sort of problems using computer algorithms, we initialize the problem with random initialization. So randomly it generates a vector which creates the initial labels, and then based on that particular random initialization, we basically solve the problem, and then we basically reach the local minima. So even in the gradient descent problem as well, gradient descent optimization. So there also you had seen that the gradient descent problem is like this, let's say. And if I just write Wn plus 1 is equals to Wn minus eta into del E by del W. So this thing we already have seen. This is called the gradient descent equation. So what about W naught, which is at the first iteration? So in the first iteration, or always you will see that we do random initialization. And then based on this, as because we are solving this through a computer algorithm, we put some eta value, and then what we do, we can see that we step by step, in a step by step fashion, we try to reach at the local minima or at the global minima. And at this particular global minima, the derivative will vanish. So this part will become 0. So that means Wn plus 1 is equals to W1. So that means everywhere in the machine learning literature, as because we solve these sort of problems using computer algorithms, we initialize each and every problem with random initialization. And using that random initialization, we solved these problems iteratively. And then we got the solution. So in that previous question, the label that they have given, so that was also a random initialization based label. And in this particular question, so the question states that how does k-mean initialize the cluster centroids? So that means if we get the labels, initial labels, then only we can calculate the cluster centroids. But how we can get the labels? So that label we can get through random initialization. And in examination
Okay.
question, in mathematical question, they have to provide some initialization. So you cannot take random guess because n number of people can take n number of random guess. So there
Yes,
will be
sir.
limit. For that, they have given the initial labels.
Yes, sir. Thank you, sir.
So in general, when you solve these sort of machine learning problems, so everywhere you'll see that random initialization is the initial guess that we basically comprise of. So let us see through other solutions, other options as well. At the maximum data point value, so the maximum data point value, this is wrong because we need the random initialization of the labels. So the maximum value of the data point could be, let's say you have three groups of data, you have to create three clusters. So that means K is ranging from 1 to 3. So you cannot put the labels as all the data point belongs to class 3. So that if you put everything to basically belong to a single particular class, then uh, even if you run through the iteration, you will get the same data label again and again. Then based on the mean of the data point, so the mean of the data point will not ensure that the label should be integer one. So for example, in this case also, uh, let's say uh, you have two class. Let's say you have to do two clusters. So therefore, your k will range from 1 to 2. So mean of the data point would be 1 plus 2 divided by 2. So this is 3 by 2, 1.5. So you can see that you are getting a arbitrary label 1.5, but data labels are integer only. So as you can see that cluster 1, cluster 2, cluster 3. So therefore 1.5 will not be an answer because you cannot say that you are creating cluster 1.5. So this should be a categorical variable or integer variable. So therefore mean of the data points is also incorrect. And at the origin it could be a situation. It could be a situation that given the data point clouds, let's say you have certain data point clouds, you can choose an initial guess of data centroid at this particular point, but this would lead to some bias. So therefore, to avoid bias, to avoid a strict definite value, like you want to put a data centroid at 0, comma 0, may create a bias. So I can show you one example. Let's say you have data points like this. Your data clouds are like this. And for this particular data cloud, you can create the possible data centroid should be this. So this could be one cluster, this could be one cluster, this could be another cluster. Now you are saying that you will put a data centroid at 0, comma 0. So it means at this particular point. So from this particular point, each and every point would be almost equidistant. So therefore, creating a data cluster, data centroid at origin for these sort of problems, for any arbitrary problem, will not lead you to the correct solution, as because this could create a bias to the problem. So this is creating a bias to problem, and the solution, this particular solution, is not uh, generic for arbitrary data cloud distribution. So you can see that over here, your data cloud is at this particular point, at this particular region. However, you're putting a data centroid at this particular place where there is no data. So how can you create a data centroid around which there is no data? So again, so this is also incorrect. So these 3 points are incorrect. So random initialization is the initialization that we everywhere do. So be it, let's say, what do you call, gradient descent based optimization technique, and even subsequent lectures in the subsequent weeks also, you will see that in case of neural network architectures and other cases also, you will see that we preferably use random initialization. And in deep learning, there are certain initialization functions, specific functions are also provided, but later on you will see what are those initialization functions that you have. Okay. Okay, the next question states that what is the best way to determine the optimal value of clustering? I think I have some internet issue. Okay. Uh, so what is the best way to determine the optimal number of clusters? So if you see these options, so in the first case, they have written trial and error. So trial and error could not be the solution. There have to be some finite way, because if it is a trial and error, so you can start with any sort of arbitrary k, and you can experiment with any sort of arbitrary range of k values. So which is not the correct answer. So this is incorrect. Now there should be some alternative method by which you can consider that what could be an optimal value of k. So let us see the third option. So the third option states that setting k equal to the number of data points. So this is also incorrect. Why? I can just pictorially show you. Let's say you have okay. So as because I do not have the labels, so I am not putting any other marker. Let's say this round one. So everything I am plotting by using this cross marker, right? So because I do not know the labels of the data, but I want to group them. So for the from the example of pen, so I told you that you let's say you have a data set of pen, and the pen variety of the pens are like they have different colors and different length. So it is our different length. So it is our normal human tendency. Let's say you if you have a bunch of pen which is scattered in your table. So what you will do, you will try to arrange those pens, and there is not a unique way of arranging the pens are present. So if let's say you can arrange them, let's say there are 3 to 4 people are there, and we have kept the pens haphazardly in the table, and we have told each and every of them to arrange them. So some of them might arrange those pens by their color. Let's say red pen, they will group them together. Blue pen, they will group them together. Some other person may group them like ball pens. They will group them together. Uh, Dot pens, they will group them together. Gel pens, they may group them together. Let's say some other person can group them based on their length, pen, the length of the pen. So there is no unique way in grouping or clustering. So therefore, uh, so the main point is basically in the first example, I told you that let's say red color, blue color, green color. Based on this, someone has grouped. Someone has grouped based on the type of the pen, whether this is a ball pen or gel pen. So now the cluster is two in this case, ball pen or gel pen. In the previous case, cluster was three, red, blue, green. So that means the K, the optimal value of K may vary, and it is problem specific, and it is also uh, heuristically chosen variable. So what is meant by heuristically chosen variable? So that means you can choose any sort of arbitrary value of k and you can start doing the clustering process. But how you can get to the optimal value of k, that is the main question. So over here, the third, as far as the third third option is being concerned, so you can see that setting k equal to the number of the data points. So that means if you, let's say, have 1,000 data points, let's say 1,000 pens, you cannot say that uh, I will group 1,000, I will create 1,000 groups of pen, 1,000 groups of pen. This is incorrect because you have to group certain amount of data points together. You cannot say that using a single data point you will create a group. So what you are meaning by this point 3 is basically, so this particular pen is a group, this particular pen is a group, so individual pen is an individual group. So that is incorrect. So setting k equal to the number of data points, so let's say you have 1,000 pens in the data set and you are trying to create a group using a single data, so that is incorrect because that is not practically rational. So therefore, this is the incorrect option. So now let us see the other options. Okay. So elbow method. I don't know whether elbow method has been taught in the class or not, because I don't think so, because elbow method itself is a uh, itself needs some in-depth analysis. So elbow method is basically relates with the sum of squared error loss. So yeah, sum of square error loss. So sum of squared error loss, it is something like y minus y hat a whole square. So y is your target, your true output, and y hat is your target output from your k-mean clustering. And this is the loss function. So you can see if you if you just break this particular operation, that is a minus b's whole square. So the equation that we'll get, this is a quadratic equation, and where the true output is basically the value that you know already, and y hat is basically the model's prediction. And the model is something which you are basically creating by changing the value of k heuristically. So that means this is a quadratic equation, and specifically this is an equation of parabola. So I can consider a convex. So this is a convex parabola. So I can consider the loss surface to be like this. And surprisingly, in the elbow method also, this we have actually a solver to, so we vary the loss with respect to k, because your y hat is a function of k, because your k means clustering, you are changing the value of k. Based on this value of k, you are getting the y hat. So that means y hat is a function of k. So we vary the k, and with respect to k, we try to see the loss function's output. And as because this is a quadratic function, so we know that the quadratic function will give you a parabola like this, a convex parabola like this, that we have already seen in case of the gradient descent based weight optimization technique. And based on this, we have a solver just like the gradient descent optimization. And using that, we optimize this loss function and update the value of k. And at this particular location where we got the minima, so over there the derivative will become 0, and therefore your update of k will become constant. So that means this is the point. This is the point where you will get the optimal value of k, and the same operation you will see that kn plus 1 is equals to kn minus eta into gradient. So gradient of L. So gradient of L at this particular position, you can see that the derivative will become 0 because this is the minimum point, and therefore this particular part will vanish. It will go to 0. So therefore kn plus 1 will be equal to kn. So that means this will give you the optimal value of k, same as that we have seen in case of gradient descent based method. So this elbow method itself is the best way to solve the k-means clustering problem. And there are some other techniques also, like the SS method, the scoring method, but the scoring methods are not that optimal. So the optimal method is basically by going through the gradient-based optimization technique. So in the case of elbow method, which basically deals with the sum of squared error loss with respect to the k, and from there we can get the optimal value of k, because it basically creates a computational algorithm which basically employs the gradient descent like architecture, the gradient descent like structure, and then from there we can get the optimal value by reaching the global minima or the local minima. So which basically gives you the optimal way to find what should be the optimal number of clusters that you can consider, and that you can start off with solving this particular clustering problem. So let's say it will create a cluster like this, it will create a second cluster like this, and this will create a third cluster like this. And you cannot choose arbitrarily large cluster values, so that they have written in option 3, that is each and every point, the maximum number of points that you have in the data set. So this is also not the correct answer, because creating clusters using a single data, that is not the correct rational thing. So we are left with question 9 and 10 actually. So in case of question 9 and 10, I have found some discrepancy. So I will talk to the NPTEL regarding the discrepancy, and then in the next week I will solve. Otherwise, I will talk to them, and then I will get to the discrepancy, and then I will solve the question in the next week.